Okay, so welcome back everyone. We're gonna finish today's channel day with Kean Chen. We'll be talking to us about, turns out, both upper and lower bounds after we have developed some of the techniques in the previous talk. And Kean, take it over.
Okay, thank you. Hello, everyone. My name is Kean. I'm very happy to be here to introduce my recent work on quantum channel tomography, co-authored with Filippo, Edo, Lenkun, and Zhichen. And my name is Kean. Okay, so let's begin. Okay, so the task here is quantum channel tomography, which is like channel analog of quantum state tomography. And you know that the state tomography is a very, as was mentioned yesterday by John and Jack, is a very interesting and important application of the random purification channel. And quantum channel tomography is also a very interesting application of the random dilation superchannel. So in state tomography, you have many samples of an unknown state rho, and you need to produce a good estimate that is close to the state rho. And so in quantum channel tomography, you have many queries to an unknown channel F, and you need to produce a good estimate of F. Okay, so in this work, we consider channel F with input dimension D1, output dimension D2, and cross rank at most R. Okay, so and the error measure we use here includes diamond norm, which serves as a worst case measure, and another is the trace norm for the choice states, and we just call it the choice trace norm, and it serves as an average case measure. Okay, so let us first consider two important special cases. The first case is the state tomography, and you can consider state as a special channel where the input dimension is D1 equals 1. And for state tomography, we already know that the sample complexity is RD2 over epsilon squared. And another case is the unitary tomography, where unitary you can consider it as a special channel where the input dimension D1 equals the output dimension D2, and the cross rank equals 1. And for this, we also know the query complexity is D1 squared over epsilon. And for these two special cases, you can see they have very different error scaling, and one is epsilon squared, which we call it the classical scaling, and one is epsilon, and we call it the Heisenberg scaling. And so the natural question is, how about the general channel tomography? How about error scaling of the channel tomography between these two special cases? And there is a related result in the literature which study isometry tomography. And isometry is also a special channel where the cross rank equals 1. And they have a lower bound of D2 minus D1 times D1 and divided by epsilon squared. And this lower bound tells us that once D2 is strictly larger than D1, okay, so we must have a classical scaling term in the lower bound. And this is very interesting and provide many intuition here. And however, this is still a special channel. This is only holds for isomer channel, and there is no dependence on R. And yes, okay. So the question is also open. So how about the general channel, or more precisely, for general channels, when and how does the query complexity exhibit Heisenberg scaling or classical scaling? So this is the main question here, and we will try to answer this question. Okay, so before I introduce the results, I need to first define a very important parameter, which we call it the dilation rate, tau, and it is defined as RD2 over D1. So we use this parameter to divide the whole parameter region into 3 subregions. And for example, okay, so first we consider trace preserving quantum channels. So for these channels, tau is always larger than or equal to 1. So when tau equals 1, we call it the boundary region. Okay, so in boundary region, we have an upper bound RD1, D2 over epsilon, and this holds for the choice trace norm. and this matches our lower bound. Okay, and this is, of course, a Heisenberg scaling term in the boundary region. And we have another bound for the diamond norm. However, this diamond bound is just a minimum of Heisenberg scaling and a classical scaling term. And this is not tied because you can see there is a overhead of square root of d1 in the Heisenberg scaling term, and the classical scaling term has matching dimension dependence, but the error scaling is not good. However, this upper bound is just improved in a recent work, and it was introduced by Marco, and we will also see later. And okay, so in the away from boundary region here, tau is bounded away from 1, constantly bounded away from 1. And in this region, we have an upper bound like this, and this holds for both Choi norm and diamond norm. And we also have a matching lower bound. So in this region, everything is okay, settled. And another thing I need to mention is that this upper bound is also independently obtained by Miller and Beetle in their work via a different method. In fact, they obtained this bound in the whole region, and this bound is tight in the away from boundary region.
Sorry, so that bound is diamond norm?
Yeah, this holds for both diamond norm and Choi norm, both upper and lower bound. Yeah. So this is in this region, everything is solved for diamond norm and Choi norm. If you only consider dimension parameter and error scaling error parameter, yeah. Okay, so the third region is a little bit complicated and a little bit difficult, and this is the near boundary region. And here tau is larger than 1 but smaller than 1 plus arbitrary constant c, and so tau can be arbitrarily close to 1. And in this region, we have several upper and lower bounds, but they are not tight here. So first, let us consider the Choi trace norm. Both upper and lower bounds are mixtures of Heisenberg scaling term and classical scaling term, and a linear mixture of classical and Heisenberg scaling terms. And tau controls the weight of the mixture, you can see. And in the upper bound, the dependence, it's linear depend on tau, and the lower bound quadratically depends on tau. And in fact, here, tau is close to 1, so tau minus 1 is close to 0. And so tau minus 1 squared is smaller than tau minus 1. Okay. And we have matching Heisenberg scaling term, but for the classical scaling term, the upper bound has overhead on d1 squared, and tau is quadratic in the lower bound, but linear in the upper bound. So they are not tight currently. However, we can still see that at least the true complexity must between those linear dependence and quadratic dependence, and exhibit a mixture of Heisenberg and classical scaling. Okay, and for diamond norm, the upper bound is also not good. This is just a pure classical scaling term here, and the lower bound is a mixture of classical and Heisenberg scaling, and it depends quadratically on tau. So I think we can simplify our result and summarize in a figure here. So in this figure, we focus on epsilon and take d1 to be a constant. So and orange and blue regions indicate where the query complexity should lie under diamond norm or Choi trace norm area. Okay, so let us so the x-axis represent the dilation rate tau here, and the y-axis is the error scaling, and this point is the classical scaling, this point is Heisenberg scaling. And so first we can look at the boundary region here, this vertical line, the boundary region. Okay, so both norm is at this point. They exhibit pure Heisenberg scaling behavior at this point, and also in the away from boundary region, they exhibit pure classical scaling behavior. And these two regions is quite clear. However, in the near boundary region, here, we do not know too much about it. For example, for the Choi trace norm, we have an upper bound, linear upper bound, and a quadratic lower bound, like here, you can see. And the true complexity is in this blue area. And for diamond norm, it becomes worse. And the upper bound from this point and suddenly change to this line. Okay, so this is a sudden change, not good. And the lower bound is better, and it is a quadratic curve here. So for diamond norm, we have a very big area of uncertainty, and but for Choi norm, the area is smaller. Okay. But we call it a phase transition because here C can be a constant that is very small, and you can see in the boundary region and away from boundary region, they exhibit totally different area scaling, so we call it a phase transition. Yeah. But in the near boundary region, the problem becomes a little bit harder. Okay. So I will introduce some implications of our result. The first implication is about homomorphy of equal dimension channels. So equal dimension here, I mean, you set D1 equals D2 equals D. That is, you have equal input and output dimension. And we just call it, for example, a D-dimensional channel. And homomorphy of such channel has query complexity Ds, and it's totally settled. And you can see that you have Heisenberg scaling if and only if R equals 1. And once R is larger than 1, it becomes pure classical scaling. And this is just because the dilation rate tau equals R here, once D1 equals D2 equals D. It must be an integer, so 1 corresponds to the boundary region, and 2 and larger correspond to away from boundary region and totally settled. Okay, so this holds for both norms, and the case of unitary tomography is in fact solved by HKOT 23 before. Yeah. Okay, so the second implication is about tomography with state preparation channels. Okay, so in this implication, we consider the boundary region, tau equals 1, and we consider task of tomography the mixed state using the queries 2E. And we have this upper bound, which is a minimum of two of a Heisenberg scaling term and a classical scaling term. And there is some related result in the literature. They study a task called tomography using state preparation unitary. And it's like you want to tomography this state, and you have query access to you. And in the paper VAC-23, they give a nearly optimal upper bound. They give a near the optimal upper bound d over epsilon, which is a Heisenberg scaling upper bound, but use both forward and inverse queries to you, and it's sequential. And their queries are sequential. And so we cannot directly use the random dilation technique to obtain the same upper bound for the general channel. Okay, however, another work by myself, it gives another larger upper bound, but use only forward queries to you, and their queries are parallel. And this upper bound can be combined with the random dilation techniques to give the same upper bound for, like channel version. Okay, so this is the second implication. And the third is about state tomography lower bound. Okay, so in this setting, in this case, we said D1 equals 1 becomes state, a channel becomes a state, right? So our lower bound implies that the state tomography requires sample complexity dr over epsilon squared. And in fact, this lower bound is recently obtained by the paper SSW25, which is first obtained the optimal lower bound for the state tomography. And our result reproduced their result using a different line of reasoning. And in fact, before the SSW25, there is a long-standing, I think there is long-standing logarithmic gap between the binomial upper and lower bounds. Yeah. Okay, so this is the third implication. Okay, so let me introduce some, the recent development, which Marco has already mentioned. And they this paper, HLS plus 26, they give a very interesting unitary tomography algorithm in diamond norm using only parallel queries. So they can be combined with the dilation techniques to give a boundary region tomography optimal one. And matches our lower bound. Yeah. So in the boundary region, everything becomes solved. Yeah. And they use classical shadow for tomography, and this I think is very interesting. Yeah. So I will talk very, very briefly about some upper bounds details. So what we use is also it's very simple if you understand, if you know the random dilation. We use something like dilation does not help with parallel queries. And it says that if you want to solve an estimation task Q and for a channel E, then access to dilation of E does not help. You can always simulate the dilation using parallel queries to E itself. And it can reduce tomography of channel to tomography of asymmetries. Yeah. And however, in our paper, we obtain this result not using a little bit different method. And this result can be obtained both from random dilation and local test. And the reason we call it local test is because at the first time we consider such kind of problem, we consider, and which is also mentioned by John yesterday, we consider bipartite state learning, something like this. So for example, we have a bipartite state on system A and B, and we want to learn something from it. And then I will use a POVM, like a tester, to measure it. And if the information you want to learn is unitarily invariant on system B, then we can always transform this global tester into a local tester that acts only on the system A and without loss of generality. And this local tester can faithfully simulate the global tester. And so this is why we call it the local test. And in fact, in this case, if you consider B as an ancillary system, and then AB is just like a purification of the state on A. So this is just like the purification does not help in this case. And so here is some relation between, I think, maybe interesting between random purification and dilation and local test. And I think they are quite like a dual concept in some sense. For example, random purification and dilation, they are transformation applied on state and channels and give you like pure state and asymmetry channels. And the local test is something like some transform applied on the tester, which is such as POVM and measurement. They give they transform global tester into a local tester, and in fact they are dual to each other with in the Schrödinger and Heisenberg picture. And one is evolution of state in the Schrödinger pictures, and one is evolution of like POVM in the Heisenberg picture. Yeah. However, there is a very important thing I need to mention is that those random purification and dilation papers, they also give explicit and efficient circuit construction here, and they provide additional operational meaning of it. And this is important. And the local test paper only give the mathematical description of this transform. And in fact, if you only care about the sample or query complexity, it's enough. But if you care about the time complexity or circuit complexity, you need to use efficient circuit construction. And also, if your task is purely quantum, that is, you do not need a final POVM. You only want to produce some quantum thing like quantum state or quantum channel, then you should use random purification or random dilation like this. You should using something in the Heisenberg Schrödinger picture. Yeah. Okay, so then this is what isometry tomography we use to obtain the channel tomography result. This tool has already already introduced by Marco, so I will introduce the first two. The first one is a unitary tomography algorithm in parallel using parallel queries in Choi trace law, and it can be linked to a channel tomography algorithm in the boundary region in Choi trace law, the same upper bound. Okay, and this one is And isometry tomography also using parallel queries in Choino, and we can lift it to in the long boundary region, where you just replace D2 here by RD2 here. Okay, so this is where our upper bounds come from. Yeah. Okay, this is the very recent development. Okay, then I will introduce the lower bounds. Okay, so the lower bounds are established in 2 stages. The first stage is to identify 2 structured family of isometries such that given a sufficiently large set of either type, the discrimination task is hard. So we have 2 types of isometry. The first is type 1 and correspond to the boundary region. And for this type of isometries, we proved some hardness of the discrimination task, which is f over epsilon. This is a Heisenberg scaling hardness, and f here depends on the dimension parameters and will be specified later. Okay, so for type 2, this is this corresponds to the long boundary region, and we prove the hardness of with classical scaling hardness for the discrimination task. Yeah. So this is the first stage. For the second stage, is to give a sufficiently large set of packing net. Okay, the second stage we construct a sufficiently large epsilon packing nets of isometries such as this figure holds. Okay, so let's look at this figure. The left-hand side is a packing net. You have many isometries here, here, here. See, and they are either type 1 or type 2. The sets are either type 1 or type 2, and we require that each pair of isometry are epsilon far from each other. Yeah. And we also require that after tracing out the ancillary system here, okay, so here you consider isometry as some dilation of a general channel. So you have the ancillary system correspond to the system that for the dilation. Okay, so we also require that after tracing out the ancillary system, then you can get many general channels, right? And this set of general channel is also epsilon far from each other. This is what we require. So if you have this, then you can give lower bound for channel tomography, because any tomography algorithm can solve the discrimination task of this packing net because they're epsilon far from each other. And then this algorithm can solve the isometry tomography, isometry discrimination task in this set, because you can just discard the ancillary system and run your algorithm. Yeah. And in the stage 1, we proved that solving the discrimination task of this subset, this set is hard. You either have a Heisenberg scaling term lower bound or classical scaling lower bound. Yeah. So this is how this is the overall idea of our lower bounds. Yeah.
And see, so like, let's say you have like a lower bound for states, right? As a special case of this, and then what you're saying is that you just have a family of pure states.
Yes.
In that case, and then it's hard to distinguish those pure states, and then like when you trace out that solar register, you also get mixed states that are fluid.
Yes, exactly. The mixed state is also far from each other. So this is what we will consider in the construction of the epsilon net. You must compute the distance of this channel after tracing out the ancillary system, and you require that the distance is still epsilon far from each other. Yeah. Okay, so this is a 2-stage idea for our lower bound. Okay. Okay, so we will first consider the first stage. So one of the tools we used in the first stage proof is quantum comp, which Marco already also mentioned. Okay, so you do not need to look at the formal definition here. We can just look at this figure. Okay, so quantum comp is a very convenient tool to describe like the interaction of quantum algorithms. And for example, in this figure, you have X is a quantum algorithm, Y is another quantum algorithm, and the environment gives a quantum state to X, and X has some compute and output a quantum state to Y, and Y has some compute and output back a quantum state to X. And this process repeat many times, and finally X output a quantum state. So either X, both X and Y are quantum comps, and here X is a 4 comp because 1, 2, 3, 4. So X is a 4 comp, and Y is 3 comp, 1, 2, 3. So a 4 comp combined with a 3 comp, you get a quantum channel from H0 to H7. Okay, so, and in fact, they are very useful because any interaction of such quantum algorithms can be described by quantum comps, and any quantum comps can be implemented by a quantum algorithm. Yeah, and they have a closed form. Definition, quantify-free form of definition. So it's very useful. And then we can define the channel tester, which is just like a generalized POVM for the channel. Okay, so a channel tester is a set of positive operators Ti, such that first, given access to channel E, we have this equality. Okay, so here I do not draw the like at left and right because Ti has no initial state input and has no quantum state output. The tester is just like a measurement. It output a classical outcome. So there is no left and right like of Ti. So Ti makes some queries to E. There are 3 queries here. And after the contraction, the final, this contraction becomes a real positive number, which is the probability that the tester's output is I. Okay, so this is the first condition. And the second one is we also require that sigma I Ti is also a quantum comp. So this becomes a valid quantum channel tester. Okay, so in fact, any tomography algorithm can be described by such a quantum channel tester. Even they use sequential and coherent queries, anything, okay. Okay, so this is important and will be used in our later proof. Okay, so then we can consider the proof. Okay, I will first introduce the type 1 case. Here, since type 1 case corresponds to the boundary region, we consider unitary, d-dimensional unitary here. And we first define V0, which we call it a center. And you will see whether, why, you will see the reason. And define perturbation delta as follows. V0 is just like an identity operator and times a scalar that is a little bit smaller than 1. And delta is like another isometry. And here, I is the imaginary unit. And this is a diagonal matrix with half +1 and half -1. And here, for simplicity, we assume D is an even number. Okay. Okay, so there is a very important property we will use is that V0 and delta are orthogonal to each other. Here, orthogonal, I mean when we flatten this matrix into a vector and they are orthogonal. Here, cat delta, here, I mean we flatten this matrix into a vector. Okay. Okay, then we can define our type 1 isometry, which is V0 plus epsilon U delta U dec. So you can look at this figure. V0 is like a fixed point at the center, and we apply some perturbation here to obtain Vu. And U controls the direction of this perturbation. U is used to control the direction of this perturbation, right? Okay, so you have many VU defined. You can define many VU. So for any, the family contains all those VU for all d-dimensional unitary for all direction. Okay, this is a type 1 isometry.
Sorry, this is an isometry or this is like a unitary?
In fact, this is unitary because this is a boundary region. Sorry. So in fact, this is unitary. Okay.
But it is normalized. Is a factor of square root 1 minus epsilon squared.
Which one normalized you mean?
I mean, is V0? Sorry. Oh, okay. So VU is a unitary.
Oh yeah, I mean VU is a unitary. Yes. VU is a unitary. Yeah. So this is but because in our paper we also consider near boundary region, so we call it isometry. So this is a small mistake in this talk. Okay. So here this is unitary. Okay. Okay, so then we can assume that we already have a set N of type 1 unitaries. Okay, so we can express the success probability of this discrimination task as follows. So this term is just represent the N queries to the unknown unitary VU, and this term represents the tester that output the correct answer VU, right? So, and this is the cardinality of N because in this discrimination task we consider the average performance, and the referee uniformly randomly pick an unitary from the set and ask you to identify it. So this is the success probability of this task, and we want to upper bound this probability. So for this, we decompose VU tensor N into orthogonal sectors. It's like we try to analyze the N queries of this VU, and if you remember, VU is the sum of V0 and the perturbation, and we just decompose it using like a binomial expansion something, yeah, and then we can write it in this form, and gamma S here is defined as follows. Okay, so here S is a subset of N indexes, and it indicates where the perturbation delta appears. For example, if S contains 1, 3, 4, then the perturbation exists in the first query, the third query, and the fourth query. Okay, so this is important. This is important because for the discrimination task, the information is stored in the perturbation, right? So we try to record where it happens in this decomposition. And another point here is that here we can write U as a global action on the whole N system because V0 is invariant under the action of U. So you can just group all the action U together and globally act on gamma S. Okay. So this is a decomposition. And then we will define the capital gamma S, which is just an average version of gamma S with all unitary, all direction U. This is an average. And definition is pretty simple. And we do this because we want to give an U-independent upper bound for all N queries represented in this is in fact the choice state of all these N queries. We want to upper bound this in the normal order, right? Okay, then we can, in fact, we can prove this inequality. That is, all these N query represented in the choice state is upper bounded by another matrix, which is the sum of lambda S and gamma S. Here, lambda S are coefficients, and in fact, we can construct lambda S so that it is finally well upper bounded. But I will not give the detail of lambda S here. So you can look at this inequality. This is important. VU is upper bounded by an operator that is U independent. Okay, so once you have it, you have this, you can do a very intuitive calculation. Here, you can look at this figure. The left-hand side represents n queries to the unknown isometry. Here, n equals 3, 3 queries to the unknown unitary. And we have just proved that when represented in the Choi state, it was upper bounded by another operator, that is by this. And in fact, we can prove that each gamma s is also a quantum comp. And okay, so then therefore, if you remember the definition of the success probability, it equals the left-hand side of this. That is, the summation is over all unknown isometry, and you have a tester contract with those queries, right? And this is in fact the cardinality times the success probability. Yeah. And then using the inequality above, you can replace those 3 queries by this operator. So you get this, right? You get the right-hand side, this. And this, remember that this operator does not depend on you. So this summation only applies to the tester here. So if you remember, the tester itself, by definition, the sum of the tester is, by definition, is a quantum comp. So this is just the contraction of a quantum comp with another quantum comp. And it becomes a scalar, which is some lambda s. And this is upper bounded by our construction, which I have not specified here, but you can, yeah, this can happen, yeah. Okay. So then we can bound the success probability. We can upper bound the success probability. And what we use is that gamma s is a comp, and we have this inequality here. So, okay, so once we can upper bound the probability, we have like this. We can also, because the success probability must be larger than 2/3, right? So we have this inequality, right? So once you have the cardinality sufficiently large, you can solve this inequality to give you a lower bound on the query number n. Okay, so this is how we obtain our lower bounds. Yeah. So this is for type 1. Type 2 has a similar overall idea, but with some important difference. And I will just focus on the difference here. So for type 2, type 2 is for the long boundary region. So we consider isometry with input dimension D and output dimension capital D here. And capital D is larger than 2D for simplicity in this representation. Oh, well, no, this presentation. Okay, so this is for simplicity. Okay, and we also define the center V0 and the perturbation delta. V0 is the same as those in the type 1, but delta is different. So you can look at this figure. V0 is just the embedding from HA to HB, and this embedding can be like arbitrary. We do not require the basis to be chosen prior to that. And delta is another embedding. You can see this, that the image of delta is orthogonal to the image of V0, and this is what we use later. Their images are orthogonal to each other. Right? Okay, so in fact, we can do some comparison here. In type 1 case, we require that V0 and delta are orthogonal to each other when it was written in vector. And this is equivalent to this formula, right? And in type 2, we have a stronger condition. You do not need to do the trace, to do the whole trace. You only need to do the partial trace on the output system B, then you can get 0. So this is stronger, and this does not hold in type 1. This is why we can prove a stronger classical scaling lower bound in type 2. And the very important point is that delta has orthogonal image than, to the image of V0. And this only happens once you have a big HB, right? You must have something, you must have a large dimension space to contain 2 images that is orthogonal to each other. So this does not happen in the boundary region. Only non-bound region or away from bound region. And in the near bound region seems is similar but with more details. Okay. Okay, so this is why we have classical scaling and the type. Wait. So okay, I will speak loud. For type 2 family, we have we define U as follow. V0 or the same V0 plus epsilon U delta. This is a perturbation, and U here is applied on the orthogonal complementary of V0, of the image of V0. Yeah. So U also controls the direction of the perturbation, and we can also verify that VU is an isometry. So this is our definition of type 2 isometry. Okay.
So just to be clear, like in the D1 equals 1 case, which is when you have when you're dealing with a pure state.
Yes.
Then all it is like you have a like 1 minus epsilon on ket 1,
Yes.
and then you just have some random thing on 2 through D.
Yes, I think this construction is very almost the same with the tomography. Yes,
Yep.
that paper. Yeah. Yeah. So in fact, this that paper is very gives our intuition for its proof. Okay, so we also decompose the query into orthogonal sectors, but the decomposition is a little bit different. Here, we also use the binomial expansion, but after this, we do some grouping. We define gamma I instead of gamma S. So you can look at this comparison. In type 1, we decompose it into different gamma S, and S record where the perturbation appears. But gamma I is the summation of different gamma S for of the same cardinality. Here, you can see. So gamma I only records how many queries happen in a computation path. How many data appears in a computation path. And after this, we can using this property, stronger property, as I mentioned earlier, we can prove that the capital gamma I defined similarly by average over those direction is a count, and this does not hold in type 1 case because you do not have this property. Okay, so this is the why we have a stronger lower bound, because you have a stronger condition. And let me try to give some intuition here. It's like, for example, gamma S in the type 1 decomposition, that gamma S is not invariant on the permutation, right? But gamma I is invariant on the permutation of tensor. And it's like, for type 2 case, the algorithm cannot get information from where the perturbation appears. But for type 1, the algorithm can learn from like something like this. But this maybe this is not correct. Okay.
Right, can I ask a question? So I'm trying to just keep the state lower bound in my head. So if we were again in the D1 equals 1 case, is there this property of it being a cone? What does that mean in like the D1 case? The D1 equals 1 case. Does it just mean it's permutation invariant?
Because you mean in the type 1 case,
Or so in the type 2 case here, in the type 2 case, you have that this gamma I is a cone. And I'm just wondering, what does that mean? What does that correspond to when you're not looking at isometries, but just states?
Let me see.
Does it just mean it's like an element of the symmetric subspace, maybe, or
Here it's just like a state, I think. If you.
It just means it's a state.
Yes.
Okay.
It's just it's state and like a particle operator or something like
Okay.
that. Yeah. Maybe it becomes quite becomes state in the D1 equals 1 case. Yeah. Okay, so finally we can using similar idea to bound the success probability, and provided we have a very large cardinality, you can solve N and get a better lower bound. So I will not show the calculation here. So this is our proof of the hardness of the discrimination task. And then
go to the second stage, how to construct the actual net. And we also use probabilistic construction, which I think is very common and popular in constructing actual net. And we use some independent randomness, which in our case is the randomness is applied on the unitary, the direction of the perturbation, right? Remember the hard random unitary. And using this randomness, we can sample many perturbation delta and apply it on V0 to get many either type 1 or type 2 isometries, V1, V2 to Vn. Right? Okay, and then we compute the expectation of the distance of each pair of channel after tracing out the ancillary system. And then we compute the expectation and we use something like the generalized Levis lemma to prove that with very, very high probability that each pair of this channel are far from each other. And then you can use the union bound to show that after sampling many delta, there is at least a positive probability that the net that any pair of quantum channel are actually far from each other. So this means there must exist such actual net. Okay, so this is the probability construction here. And another point I want to say is that, in fact, the actual net is constructed. The construction of the net quite depends on the region. For example, for type 2 hardness, we still split the whole parameter region into 3 subregions, and we define the constructions are different in each region, and I will not show the details here. But okay, so for example, and they have different guarantees. For example, the net for the Choi distance has a kappa in this distance parameter, and the kappa can be close to 0 once tau close to 1. So, but however, for diamond, because in lower bound proof, diamond is more easier, right? So there is no kappa in the distance, and also in the kinetic, there is no kappa in the for kinetic. Okay, so due to the time limits, I will not go through details of the construction. One example is that, for example, in this region, we can our construction is as follows. For example, the blue part is the V0, the center map. This horizontal bar represent, both horizontal bar represent the input space, and this square represents output space. And the horizontal axis represent R-dimensional space, and the D2, the vertical axis represent the D2 dimensional space. And this is embedded from the input space to the output space, right? And how randomness is applied on the image, just as what we see before. Okay, so this is some construction, and I think I will not I do not have time to talk more about it. So let's go to the discussion. And I think there are 2 interesting questions. One is the matching upper. One is very straightforward. Is there any way to give matching upper and lower bound in the near bound region? Okay, and the second one is that can we find another parameters other than close rank, because you see that tau controls error scaling in our result. Tau the dilation rate, and tau depends on kappa, or whatever. Tau depends on the close rank. However, you can consider special case where you have a channel with equal input and output dimension, and the close rank is very high. But however, this channel is also very close to unitary. Can we still get passive scaling? So maybe unitarity is another parameter that can control the error scaling in quantum channel tomography. Okay, thank you. This is all. That is it. Thank you.
Any questions for?
I'm sure like one of the earlier tables where you had like the upper and maybe lower bounds for the near boundary and hot near boundary or something. It was about like 1/3 of the way through, I think.
near boundary.
Maybe around here. No.
Uh,
Yeah.
yes.
Oh, yeah.
Yeah.
Thanks, yeah. I'm curious, like for the upper bounds in diamond norm, usually like in this case, you actually like prove like a stronger bound for like a stronger norm, and then you convert it to diamond norm. Does that happen here, or you really prove something with diamond norm?
Stronger bond. What is a stronger bond? Stronger norm.
Like a more strict measure of closeness than diamond norm. Like, you know, if diamond norm is like the analog of like trace distance, then like usually for the state tomography, you actually learn something better than trace distance, like infidelity or something, and then you just convert it to trace distance for whatever reason at the end. So I'm wondering if it's similar things happening here, or like the actual proof achieves something better than diamond norm, but then you just decide to convert to diamond norm.
Oh yes, that's it. I haven't think of it, but maybe there may be some other norm that can be dealt with and give a diamond norm one. I don't know. Sorry. Yeah.
Any other questions?
Yes.
Do you have ideas of families of channels that you would find in these boundary groups, like properties or explicit properties?
So
I mean, you can characterize this near boundary in this way. But do you have examples of interesting channels?
Oh. No, I don't know. Interesting. You mean some example? Or?
Yeah, I don't know. I mean, it's like it's difficult to find an interpretation of what it doesn't need to be in the boundary.
Okay, I see. So for first, boundary is very clear. You have unitary, right? And trace out the output, sum of the output. And for near boundary, it is like maybe you can consider everything as a unitary, right? And in this case, you have no fully controlled input system. Then it becomes an isometry, right? So maybe in near boundary, you just lose a little bit in the control of the input system. Then it is near boundary. And if you lose very many control in the input system, then it becomes away from boundary. So I think this is like.
Yeah, for example, I mean, if I was in the UBL, we fix upside to the 1/2, and maybe you can find a sequence of channels there and you have stop.
Okay. I think I do not have a clear idea.
Okay, just
Thank you.
Any other questions? Well, let's thank the speaker.
Thank you.